Welcome back to System Software. So today we are going to finish up our introduction to the compilers part of the class. Once we come back from break, we're going to dig into the details of actually compiling. But today I'd like to go over the language that we're going to be compiling. It's going to be an intermediate representation, a kind of simplified version of C or an abstracted version of a machine code. And then I'll show you what the compiler looks like, kind of go over the overview of what the project is, and then go into a little bit of the compiler framework called Antler that we're going to be using. So hopefully everyone read, I'm sure everybody read all of the stuff on Antler that I had before. If not, you can use that as review material, but that's the tooling we're going to be using for implementing our compiler. All right, so before I get into that, let me first ask questions. So into post was due Monday, so hopefully that went more or less smoothly for everyone. There wasn't a lot of people in office hours, so hopefully it went okay. And today the processes project is due. So any questions on the project? Questions from last time? Everybody good on the project? Yeah. I think I said it in the project. I think generally you can stop. Yeah, I'm not going to test like multiple inputs. So yeah, if you get a failure of any kind, you can just exit. You can also just continue to the next prompt. You can just do continue and go to the next while, iteration of the while loop. So it should be fine to do that. I'm only going to test one line at a time for execution of the program. Yeah. Yeah, if you want to, go for it. Yeah, if you're doing multiple loops, yeah. You probably also have some memory cleanup you might want to do, but you can kind of skip that.
Whenever I'm reading competitive programming, I always try to include a go-to in my solution.
You never read Go To Consider Harmful? The classic spaghetti code.
So whenever I can, I always go for it.
Well, it's equivalent to using the constructs. And in fact, if you look at like GCC, a lot of compiler code, text processing code, go-tos aren't that uncommon. You'll see this.
And it's the easiest place to break out of the nested loop.
Yeah, that's true. You'll see a lot of this style in like text processing or state machine type stuff, where there'll be a giant switch statement. And there'll be go-tos or breaks to get out of it. It's like an infinite loop, but yeah. Anyway, if you want to ever take a look inside like GCC's code base. Other questions on the project? So yeah, if you're not doing like careful memory safety or you're doing spaghetti code, that's fine. It's not a huge program. I'm not checking for like memory leaks. Just gonna issue one. You saw in the test cases, that's how they're all gonna operate. Just issue a single command. The loop is just so that it looks like how bash prompts work. They just continuously prompt for new input. All right. Okay. So hopefully everybody's good on the processes project, or maybe you're taking advantage of the regrading. Just be aware if you're leaving everything to the end of the semester, there still is at least a deadline. There's this final project deadline. Because got to submit grades, got to finish grading. So just be careful if you're leaving everything at the last minute, and you'll lose a few points. All right, let's go over the homework from last time. So last time we talked about how your source code gets to be a running program on the machine, and as you hopefully recall, there's a lot of steps to this process. There's a lot of pieces of tooling and machinery and system conventions that work together to make sure that single line Hello World program will actually be able to execute on your machine. And there's thousands, maybe millions of lines of code that actually go into making that possible, just in terms of software. Okay, so let's go over the homework. Is it the compilation phase alone that produces an executable program? Who says yes? Yeah. If you don't have an operating system, sure. Yeah, that's true. Yeah, if you don't have if you don't have an operating system, and maybe you had embedded assembly, you'd probably still need to do something to load the code, right? But yeah, it is an executable program. So in our context, we show using an operating system. Okay, what about number 2? What phase discussed in class matches function callees and callers? So is this the pre-processing phase, the compiler phase? Yeah. The linking phase. Yeah, so in this programming ecosystem, when you write functions in separate C files, that header inclusion doesn't actually give you the implementation by convention. What makes sure that multiple C programs, multiple C source files that you translate into machine code, what makes sure that callers and callees are matched up is the linker. And that's why you get, if you don't write the main method, the linker by default tries to link with the C runtime, and it's the linker that complains there's no main method. But the compiler doesn't care. The compiler will just translate whatever functions you give it to translate into object code. Questions on either of those two? All right, number 3. Does the standard IO.h file contain the implementations of printf or other standard IO functions, or does it not contain the implementation? So who says yes, contains the implementation? Who says no? Okay, good. You learned about the preprocessor. So yeah, the header files, they just contain declarations by convention. They just contain declarations. And it's what part of this tool chain actually makes sure those functions exist in your executable? The linker. Right, the linker, or maybe the dynamic linker. All right, questions about this? Questions about last time? Yeah.
I know that a phase that matches callers and callers is like the phase is the linker, but in the notes, it's a little misleading because in the notes it says preprocessor and then it says callees and callers. So,
in these notes? Oh, because the name of the file is callee and caller. This part?
Yeah.
This was that example that I showed last time, where we wrote code that had a callee and a caller. This is more just like notes on the example that I had in class. Yeah. But yeah, I see the notes. Yeah, the notes don't have all the information you need to answer these, but hopefully the lecture video does. Which I only uploaded it today. All right. Other questions from last time or on the projects, homework? Okay, so let me first give an overview of what the project you're going to be implementing for the rest of the semester will be doing. So remember that in this tool chain, we had the preprocessor, the compiler, assembler, object linker, and loader. The compiler part, strictly speaking, is just the part that takes the source code and converts it into assembly or machine code. And we're going to write a compiler that does this. It takes source code not in C, in a simpler language, and it's going to produce assembly. We're not going to produce straight machine code. We're not going to produce object code. And we're going to rely on the rest of this tool chain that already exists on our Unix-like systems to create a runnable program and load it for us. So we're basically going to be doing this part of the tool chain. And the rest of it, we're just going to plug into the existing tool chain. The consequence of this is that, we can just leverage all the existing code. You could even call C library code and other library code. You don't have to write an assembler, you don't have to write a linker or a loader. But that also means we need to follow those conventions. There are specific conventions for how machine code should be linked together and how functions should be called across compilation units. These are called the application binary interface, the ABI. And so we're going to have to learn that And it's little down to the nuts and bolts, a little nitty gritty, but it will allow us to take advantage of this entire tool chain. And it'll also show you how this tool chain uses conventions to work together to make this massive set of tools work together in concert to give you library code and let you exploit library code and easily create executable programs from source code. Okay, so the compiler part looks like this. We're going to be taking our input language, it's going to be a language that I designed for this class called Simple IR. IR stands for Intermediate Representation because it's not going to be as full-featured as a language like C. It's going to be a much simpler language. It's going to be much easier to translate, but it's also harder to program in. So we'll go over this language, but it is a much simpler language. And then your compiler, which is going to be called CodeGen, is going to read this language in. It's going to read text files in this language, and it's going to produce Intel x86 64-bit assembly code. So this is also a text file. This is those .s files that I showed last time. And remember, this program, like we talked about a week ago, this program is taking as input another program in the simple IR language. That's what a compiler does. It takes as input programs, and it's going to generate a program. What makes this confusing is that we also write CodeGen in a programming language. So we're going to be using C++ as the language for our code generator. That's because the compiler tooling we're using, Antler, targets C++. But as long as you know C, I'm going to give you all the C++ stuff. So you'll be implementing the parts that generate the code in a C-like language. You'll be able to use all your knowledge from C to be able to write code. And it's going to use the same kind of architecture that we talked about when we went over parsing. So as long as we have a grammar for our input language, we can define a compiler like we did a week ago. For each construct in the language, here we've got plus and minus and just numbers. The Antler toolkit will allow us to write code that gets triggered every time we see a construct in the input language. And in that code block, we're going to write code that will generate assembly code. Just like we did here, where when we saw a plus operation in the input, this piece of code gets run, this semantic action gets run, and the implementation that we write in the semantic action is literally generating a string. It's generating a string in the postfix array arithmetic expression language. Questions on this? Vaguely remember this part? And we're going to expand on this to take a larger language that not only has arithmetic expressions, well, it doesn't have arithmetic expressions, it has single arithmetic operations, but it also has branching, conditional branching, it also has pointers. And we're going to read that language in, and every time the Antler toolkit triggers on a construct, we're going to write code that will generate assembly output. Does this sound like fun? You're going to actually be generating code. So the confusing part about this is that you're writing a program, but that program, in the program, will literally have print statements that will spit out assembly code. And so what you have to wrap your mind around is that there are three different languages you're working with here. You have to know about the input language, you have to know enough about the output language that you're actually spitting out, and you have to actually write the instructions that will generate this code in yet another language, in yet a third language. And one thing that I want to contrast here is we contrasted the difference between interpreters, where the code that gets triggered, the semantic action that gets triggered on each construct, actually runs a function to compute the resulting value, we're not going to be doing that with the compiler. Our functions are going to be literally spitting out strings. They're going to be spitting out new code, generating code. And so that's, I think, probably the most confusing part about writing compilers, is that we're not trying to write code that computes the value of the input language. We're trying to write code that will generate new code in a different language that is equivalent to the input code. All right, questions on this so far from a high level? And I think this is actually pretty fun to do. You have code that's writing code, gets really meta really fast, and it's pretty fun. Yeah?
So, program, is it just going to output the assembly, or is it going to like output the assembly and then call the assembler and then output the binary file, or like is that something that you just have to do in like a separate?
You'll just do that, yeah, separately. Okay. So very simple architecture. It's just going to fit into this, like what I showed before, that tool chain. So we're going to use the existing tool chain for the rest of that. So we're literally just going to spit out assembly, yeah.
Okay, so yeah, it'd be simple to just like write like a batch script that would like also call the assembler, but we're not.
Yeah, you don't have to. You can do that if you like on your own, but my test scripts will do that. And maybe, well, I haven't written the test scripts yet, but once I do, that'll probably be in the test script to do that. Because I'm going to test this by not checking the exact code, because there's many ways to write the same program. I'm going to check this by running your program.
And is the IR query complete?
Yes, I think so, yeah.
Can we write another compiler in the IR?
Could you write a compiler in the IR? Conceivably, yeah. The hard part is I/O, but you can actually link. Yeah, you could. You only have integer types. I'll go over this language, but you only have integer types, so it'd be pretty onerous to do that. But you could.
Everything is just bytes under the hood.
It is. So you probably could do that. Yeah.
Represent any structure data type as just an array of bytes.
Yeah, and the language supports pointers. So you can call C functions with it. Because we are integrating with this existing tool chain, you can actually call C functions from within your compiled language. And because using the system linker, you can link to C functions. And so you could technically, I think, write a compiler. Yeah, you should be able to do that. I'm trying to think where the limitation might be. Yeah, as long as you can allocate a big chunk of memory, yeah, you can. It's effectively Turing complete. So if you'd like to do that as a bonus project, that would be very fun to see. You could compile a smaller language, maybe.
Or we could write a C to IR compiler.
You could write a C to IR compiler, yeah. So this is I didn't I forgot to put this slide in here. I can't remember if I showed it in this class. Just to give a little background on what an IR is. Did I show this diagram in this class?
Yeah.
I did, right? Okay. So the idea, so this is to kind of review what IR is, intermediate representation. It's a language that is simpler than typical input languages like C, but also less machine specific than assembly languages. And the purpose of it is to abstract away the language processing part, the input language processing part of a compiler, from the machine code generation part of a compiler. And so to make it makes writing compilers simpler, because if we have 5 input languages and 5 output machine languages, well, that's 25 different compilers we need to write. If we instead generate 5 different compilers to IR, then we only need to write 5 different back-end parts of the compiler to generate machine code. So we've got 10 half compilers kind of to write, instead of 25 full compilers. And also to make the project a little simpler in this class, instead of going from C to machine code, I'm going to have us go from an intermediate representation to machine code. So we miss some of the more fun parts of front-end processing of the language, but we get the back end, and we see the integration with the system, which I think is probably more interesting for this class, more useful for this class to see. So we'll have a much simpler language. It's not the LLVM IR. It's one I invented, kind of a teaching one, called Simple IR, Simple Intermediate Representation. So let me show you first what this looks like. Let me make sure I'm not missing something. Oh, I went back too far. Okay, so let me show you what your compiler will look like. So here is the smallest possible input language, instance of the input language. So I give a .ir extension. The extension, remember, does not matter to the file system or to any of these tools. And so this is what the IR that I've given you looks like. You have a way to declare a function, and you can return stuff from that function. There's other things you do. I'll go over the language today. And unlike C, you can only define one function per source file, just to make things a little simpler. And this is how you run your compiler. You'll write a compiler that builds a program called CodeGen in this CAPS case. And I'll give you a template for this, but it'll either read in one file on the command line or read it from standard in. And it'll emit assembly code, Intel x86 64 assembly code. And this is what it looks like. And so this is basically the template, and I'll give you a bunch of the code for the template for the assembly as well. But this is like the smallest program that can be produced by our IR language. So questions on this? So you can see this is our input. Our program takes this input and it spits out an assembly file. Yeah.
The program can be translated in many different ways.
Yeah.
Is it possible that you run the same program that gives different outputs? Or
Do you mean non-determinism, where we run this command multiple times and we get different outputs?
yeah, but they all run the same.
I mean, it's possible. That's a confusing compiler to write. So that's non-determinism, where every time you run the program with the same input, you get different outputs. You could have kind of a probabilistic compiler. And actually, in practice, there are compiler techniques that do optimization statistically, so it is actually conceivable that could happen. But I imagine that for your compiler, if you follow the instruction that I have, will be deterministic. But you may have different output from other people's compilers. So to make sure, so that when I test your compiler, I'm not just going to it wouldn't be correct to just look at the exact assembly output. I mean, you might just have different white spacing. I'm going to run your code that you produced for various inputs. And so I'm going to basically have a test suite that will make sure that your compiled program assembles and links correctly and then runs with the same inputs and outputs. So like one definition of equivalence between programs. So, in this bigger diagram, we're not just inputting, not just inputting arbitrary inputs, we're inputting syntactically valid IR, a language that is correctly written, and we're outputting assembly code that is equivalent to the input code. And one way to talk about equivalence, there's like a couple ways to talk about equivalence, but one simple way that I like to use is that if you give inputs to this language here, because remember, these are programs. So these programs themselves, if they had a machine to interpret them, then these also take their own inputs and have some output from running that program. And similarly, assembly code can be interpreted on an Intel processor, and you can give it inputs and it'll produce outputs. So equivalence, one way to state equivalence is that for all inputs, the same input gives you the same output in both programs. Now, C and other input languages to compilers typically aren't being interpreted. You don't usually have a machine that you can run them on. I mean, conceivably, you could write an interpreter. So we don't have an easy way to run the input language. But I'm going to compare it against my own implementation of the compilers, which I will assume it hopefully is correct, and I'll just like hand check the inputs and outputs that I tested on. I'm also not going to be testing on every possible input because in general that would be infeasible. But I'll give like a selection of inputs that kind of traces each path of your program to make sure that in every input where there's a difference in the program, the output's the same. Does that kind of make sense? So I wanted to kind of emphasize this part because this is the most confusing part about compilers, is that you're not trying to run the program, you're not trying to find its output, you're trying to create a new version of the program, a new implementation of the program in a different language that will run the same way at runtime. Bless you. And so for things like addition, this is a little easier to reason about. We showed this we wrote a really simple compiler in class where we took in ASCII number, the ASCII symbol plus ASCII number, and generated Intel assembly. But once we start getting into function calls and pointers and much more complicated to reason about language constructs, this distinction will become really important to remember that you're generating code that when run will do the same thing as the input language. Especially when you have, say, branching, where if you've got a conditional here, branching here, you need to generate code that's going to work for all potential paths from that branch, not just one of them. All right, so questions on this? So for the same inputs, you get the same output. And that's a strategy you can use to at least test your compiler, is that once you've generated the assembly, you can build and run it and give it some inputs and check the outputs and make sure it matches the program that you ran at the beginning. So you're going to have to kind of run the input program in your head. And I'm going to explain to you the language today. It's a pretty straightforward language. If you know C, you know how simple IR will work. So you can kind of run this in your head, and then you can actually physically run the assembly code on Eustace or on a Linux machine because it integrates with the assembler and the linker and loader to actually make executable programs. And you can even link with C programs, which will do I/O for us. So there's no I/O here. Just like in C, there's no I/O instructions. You have to rely on externally defined functions to do I/O. All right, so questions on this picture, questions on the task, your mission for the second half of the class? Or you're all puzzled? Either you're very puzzled or very excited. I hope you're excited. Excited, good. Okay. All right, so let's take a look at this language that I've devised for you to compile. So here's an example C program. You're not going to have to compile this. I just want to motivate how simple IR works, how this language works. So hopefully this is pretty clear to all of you. You've got your main method. We declare two variables, x and retval. We assign x to be the return value of this function call called readInt. I'm going to give you, this implementation isn't shown here, but I'm going to give you an implementation of this that uses scanf to read in an integer. And then we call this other function printInt, which is just another C function, and I'll give you an implementation of that. That will just call printf to print stuff out. And just like printf has a return value, so we can save that retval. And we have a return 0. So this main always returns 0. Questions about the meaning of this C program? There's no tricks here. I just want to make sure everybody's on the same page with what C does, what C programs, how they behave. Okay, so let's look at the simple IR equivalent of this. Say we had a compiler from C to simple IR. This is what the simple IR program will look like. So as I said before, one simple IR file has one function. Unlike C, where you can declare multiple functions, define multiple functions in the same file, this is the entirety of a single simple IR file. That just makes things easier to compile. The first line should always be a function name declaration. So you just say the keyword function and you give any name to the function that you'd like. So just like here in C, C is a little different. You put the return type and then the name. And at the bottom of the file should be the keyword's end function. And those are always the same. They're just keywords. With me so far on this? So these are kind of like the curly braces and the name of the function. Now, there's no type declarations in this language. In simple IR, everything is a 64-bit integer. Again, that makes things simple. But there's no type declarations of any kind because everything is the same type. Now, unlike in C, we don't declare parameters first. Instead, we declare the local variables first. And this, perhaps unfamiliarly or confusingly, includes the parameters as well. Because if you look at a C program, these parameters may be listed syntactically differently, but these are really just local variables, right? They can only be used within this function. They're declared by the function. So they're just really local variables. And so you can see here, this local vars statement includes all of the parameters and all of the local variables. And we've got params. So what params does is it says, of the local variables that you've declared, these two, argc and argv, these are parameters. So it seems a little backwards maybe. It's a little closer to the old-fashioned C, the K and R, Kernighan and Ritchie C, where the parameters were declared a little bit more like local variables. And this is done, again, to make compilation easy. So almost all of the design decisions here are around making it easier to write a compiler for this language. But I just want you to be aware that you have to declare all local variables, including parameters, at the head of this function. All right, questions so far? Yeah.
If you can explain it briefly, why do you need to tell the function or the program otherwise that these local variables are parameters?
So why? So this will have to do, after the break when we talk about how to implement functions, your compiler will need to generate code that will allocate space for local variables. And the parameters are local variables, so it's convenient to have them to know how much space you're going to need to allocate all at once.
Well, the local variables make sense, but why do you have to say these ones are parameters?
Oh, why parameters? Because if somebody else is going to call this function, then other functions need to know how to give you parameters to your function.
So that's not for the contents of the function, that's for whoever's calling it or stuff.
It is, but we have to generate code that will input those parameters from the caller.
Right.
So the caller and the callee need to have the same convention about parameter passing and return values. That's called the application binary interface, the ABI. We'll go over that more next time, but that's why I have parameters separated here as well, so that we can generate code that will process the parameters from the caller. And yeah, the ABI is probably, that and pointers are probably the most confusing parts about generating assembly code. Okay, so with that we have some much more probably familiar looking constructs. We've got assignment. I use a slightly different character for it. It's colon equals. So for instance here, this is how we would do an arithmetic operation. Now unlike C, we don't have arithmetic expressions. We can only do a single arithmetic operation at a time, just like in assembly. So again, that's for ease of compilation. So we don't have to do any complicated parse trees and try to traverse them, try to make temporary variables. Presumably the compiler from C or another language will have generated temporary variables for us. But each arithmetic operation can only appear one arithmetic operation per assignment. Questions on that? So no x times 2 plus 1, you'd have to do x times 2 and then a second assignment that uses the result of that to compute the result. So if we want to have, if in C we have something like 2 times 3 plus y, in simple IR and in assembly we'd have to do some temporary variable. Well, let's make it not have constants. And then we'd have to write code like this in simple IR. Make sense? So this is much easier to compile, basically. Okay, then we've got function calls as well. So function calls look a little different. Just like with arithmetic operations, if you want to have a function call, that's the only operation you can do in your assignment. So you can't do, print int plus 7 times 2. They're not part of arithmetic expressions. You can just do a single call on one line of simple IR. And you always collect its return value, even if you don't think it has one. To do the call is a keyword. So you put the variable that will hold the return value of the call on the left-hand side of the assignment. You use the call keyword, give the name of the function you'd like to call, and then a list of parameters that you'd like to pass to the function. So remember when we talked about separate compilation, we were actually able to compile the callee, or the caller, the function that's calling the C program that's calling another function, and we never even had to declare the function. The C compiler would just be like, okay, I'm just going to assume you have a function call here. This is because when we actually compiled it, the compiler had no problem with generating code that calls a function. It was the linker that resolves that. So here, it's no problem for us to just generate code that will call printInt by name, even if there's no implementation of it, and even if there's no declaration of it. Because this language is not typed, we're not going to actually check whether the number of parameters is correct. It's going to be up to the user. And so we're literally just going to generate the equivalent of a branch to the printInt label. And it'll be up to the linker to make sure that those addresses are lined up. So this is what also benefit of kind of integrating with an existing toolchain is we can take advantage of the same compilation strategies that C uses. Okay, and then we have a return. The return is mandatory and can only appear at the end of the function. So I know in C you can write returns anywhere, but in the assembly code they're all just going to be going to the same point in the program. All right, questions on this introductory version of Simple IR? Yeah.
So for the variables, will we have to declare how much bits are going to be allocated for each variable? Or?
Oh no, so each variable will be a 64-bit integer. So yeah, no precision, no types, no typing. Everything is the same width. Again, makes things easier. Yeah.
Why is there a local bars and a parameter?
So this is to make. We'll see this next time we talk about functions, but when you for local variables, without any additional optimization, the simple way to implement local variables is to just allocate space and memory for each variable. And this is different. This is independent of reading in parameters to the function. So if you sort of accept my argument that parameters are just a different type of local variable, then this statement allows us to generate code that will just allocate all the space we need for all our local variables in one instruction, basically in one instruction. Params will allow us to generate code to read in the parameters from another function. That's why I have them separated. And so params is always a subset of local vars. If it's not, it's a type error. There's no type checking here. We just trust the user. The program will just break if the user uses the language incorrectly. But as a bonus project, you could write a type checker here to make sure that params are being used correctly, that variables are being declared ahead of time. They might not be declared ahead of time. Yeah.
So for local vars, we can put in every single variable that we're going to use.
Yes, every single variable. So if you have a lot of arithmetic operations, you have to declare every single one of those variables. And I just realized that I changed the language a little bit this semester. So I changed the language a little bit. I changed some of the keywords and a little bit. So I think it's actually now local variables, camel case, and parameters. So minor thing. I'll give you examples of it with the project that will run correctly. Okay, so each file in Simple IR is one compilation unit. So there's just like in C when it generates code, it's one compilation unit that can be turned into a .o file. But unlike C, each compilation unit only defines a single function. Again, this just makes compilation easier. So yeah, this is the minimum that we need for a Simple IR program. You have to have end function, you have to have a return, and you have to have a function. Main, the name can change. You can have different function names, and you can have different return values. You can also return a single variable, but return cannot contain expressions. It can't contain function calls. It can only return either a literal value or a variable. So kind of in keeping with the lack of arithmetic expressions, the only place you can do an arithmetic expression is in a statement like this, is in this operation statement. Okay, so this is just like a template if you have local variables. We kind of went over this already. All right, so let me go over all of the statements that are available in the language. So you can assign constants to a variable. That's one type of statement. And you can assign variables to the value of another variable. And these have the similar semantics to C. So this takes whatever the value of x is and now binds it to y. Questions on this? Yeah. Yeah, you can have multiple digits. So these are 64-bit numbers. The compiler will just take the ASCII code and just put it in as an immediate value in the assembly. So one benefit of generating assembly instead of machine code. But yeah, you can use arbitrarily long ASCII digits, or ASCII numbers. Questions on this? Yeah. Floats and double? You would have to kind of write, so the compiler doesn't generate any calls to float, so modern processors have like float operations built into hardware. You'd have to write code yourself that models floating point with integer, if that makes sense. So this is effectively what floating point hardware does, is that did you learn about like the floating point representation in binary? So there's a convention for that, right? There's no one way to represent floating points. So you could kind of do that convention on your own, or make your own convention for floating point numbers. Like say you have the mantissa and the exponent. You could have two variables for that, and then write algorithms for doing all the operations for it, which is what people used to have to do before they had like a math coprocessor or a floating point built into a machine. Does that answer your question? So yeah, you only have integers, but theoretically, that's what the processor has. So anything you can do with the processor, you can do with integers. So that also means you can do ASCII code, right? Because ASCII code is just integers. But yeah, good question. So like maybe take like a theory of computation class if you're really interested in these kind of computation principles, how you can just, the sort of minimum language you need to do all the computation that we do with our programming languages. And so yeah, it turns out that just having numbers is enough for computability. All right, good questions. Okay, so arithmetic, it's a single operation, there's no arithmetic expressions, and it always assigns the result to a variable name. So you couldn't just say x plus 2 by itself. You'd have to say some variable on the left-hand side gets the value of the single arithmetic operation on the right side. The operands can either be literals or they can be other variable names. So hopefully this is pretty straightforward, but once you actually have to code in this language, it's a little bit more painful. Questions on this? Questions on the assignment?
You said that's not how you would do it.
No, this is,
You said you'd have to write sum x equals, or are you saying that's the assembly?
Sorry, say again, that's not how you do what?
Were you saying that that's like not the right way to do it?
This? No, this is IR. This is IR.
That is the right way.
This is the right way to do it in IR. Yeah. Sorry if I said something confusing. So yeah, you can reference, just like in C, you can mutate the same. You can have the same name on the right-hand side as the left-hand side, and it has the same semantics as C, where you get the current value of X, add 2 to it, and then reassign X to be whatever that new value is. Okay, function calls. Works just like a C function call. You don't need parentheses. There's no typing or type checking. You always have a variable to store the result of the function call, even if it's void. You use the call keyword, the assignment notation, the call keyword, and then whatever the name of the function is, followed by 0 or more variable names or numbers. So you pass the parameters just in a white space delimited list. And so recall that in the compilation phase, we don't need the definitions of these functions. We just call them. We just branch to an address given by this label. And it's the linker that will resolve that address for us before execution. Questions about this? Questions about function calls? Okay. All right. Let's get a little more interesting here. So here's branching, conditional branching. So there's no if statements or while loops. There's no block structured programming at all. It's much more like assembly. So I think everyone's done MIPS at least. So this should look pretty familiar. So the way this works is you have the if go-to keyword. Then we have a relational expression. And just like all expressions in here, there's no arithmetic expressions. It's a single operand on the left, a single operand on the right, and a single operator, a single relational operator. You effectively compute the Boolean value of this condition. If it's true, you jump to the label given after the goto. So this label can be any name. This expression, or this relational operation, can be any of the 6 relational operators. And if this condition is true, we branch here. We start executing code at this label, omitting execution of this line. If this condition is false, then we go to the next line. We don't branch. We don't follow this goto. And just like in assembly, if I execute this instruction, what's the next instruction that gets executed? After this instruction. So this condition is false, then I go here. Where's the next instruction in assembly? Yeah. The end label, yeah, it'll go to the end label anyway. So that'll be kind of an important distinction when we try to implement if statements and while loops. All right, so we will have pointers in this language, and it'll actually implement code that will generate assembly that works with pointers. So this will get a little bit onerous, especially if you're a little scared of pointers, but I think it'll give you a very deep understanding of pointers and actually make them simpler. Once you see how they're actually implemented under the hood, they're a little bit easier to reason about, I think. So these operators work very much like they do in C. Ampersand, what does ampersand do in C? Does anybody remember, or did you learn this? What's that? Takes the address, yeah. We get the address of X. And what that means, you kind of learn in a little, you have a mental model for C, and you kind of learn in an abstract way what that means. We'll see in the compiler what that means literally in the machine. We'll generate code that will actually get the address in memory that is holding the value associated with X. So ampersand gets the address of X. In C, what does this code do? Dereferences T, yeah, so T1 is assumed to be a pointer here. It holds a memory address. And this dereference will look at the value of that memory address. Not look at the value of T1, it'll get the value of T1, and then use that to do a lookup, to do a load from a memory address, and then store that value in T2. And what about this? So this is L, this is 1, 1, this is 11. What does this do in C? Assigns to the memory location pointed to by T1. So T1 is a memory address, and this doesn't So, and there's a memory. So that what's confusing about this is T1 itself has a memory location. Inside that memory stored in there is an address. That's the address that 11 gets stored to, not the address associated with T1. So we'll get this closer to the end of the semester. This is probably the most confusing part because you got to think about pointers, and then you also have to think about assembly code generation of code that will behave equivalently. But we'll get there. We'll get there later. All right. So let's take a larger example program here, and I'll just step through computing an exponent. Okay, so we have our function. This function is called exponent. We have our function name declaration and the end function here. Notice that we've got a return at the end of the function. That's the only place it can appear. We've declared these local variables, base, x for exponent, and result. And we've declared these two parameters. So just remember again, the parameters are a subset of local variables. All parameters are local variables, not all local variables are parameters. Okay, so what does this code do? It stores 1 into the result variable. We have a label for the next instruction. We do a conditional branch. If the exponent, and where's the exponent come from at this point in the program? Yeah, it's an input parameter, so whatever its value is, if it's less than or equal to 0, we're going to branch to this end label here. And what's the next instruction? The next instruction will be a return, and we'll end. So if we give an exponent that's 0 or less, we just immediately branch to return to the result. Okay, but if it's not less than or equal to 0, we do this assignment. Oh, and I forgot, I messed up the syntax myself. Look at that. Result will be assigned to whatever the result was previously times the base, and then we'll subtract 1 from exponent. Questions about this? This kind of classic implementation of exponent. Processor doesn't have exponentiation in general, so you have to implement it in software if you want it. And so once we've computed result times base and subtracted 1 from exponent, we branch unconditionally to top. I think I didn't show unconditional branches, but yeah, goto by itself is an unconditional branch. Let's say exponent is greater than or equal to 0. When will this program not branch to the top? At which point? So, yeah, x is less than or equal to 0, because this will branch past all of this code here. It'll branch past all this code. Questions on this? Questions on this implementation? So you could write this in C, because as some of you like using gotos, you could just use gotos and write almost this exact program in C. And incidentally, this is, if you were to write a while loop, so this is the equivalent in C to writing something like this. So we're not going to write the compiler to do this in this class. That's what we want to do as a bonus exercise. But compiling while statements generates code that looks like this. This is what a while statement, how it's implemented in machine code. It generates a conditional goto that skips over the body. So it inverts, oops, I did this the wrong way. So it inverts the condition and only branches away from the loop, over the loop, if the condition here is false. Otherwise, it executes the body and then repeats. And notice that the top happens before the evaluation of exponent, before the evaluation of this condition, because the condition gets reevaluated every time you run the loop. But anyway, more for graduate compilers to actually take these higher level constructs and turn them into machine code. Questions on this? Questions on this example? Yeah.
When you if statement, after the conditional, is it always going to be a go-to and then label?
Yeah, it's always going to be go-to and then a label. Always go-to and label. So it's not even strictly an if statement. It's much more like a compare and branch in like MIPS or an assembly language. And that's how we're going to translate it. We're going to translate this to compare and branch in assembly. So there's no block structured programming here. You can omit end if you want. Your program will break. Your assembly program will break, but and you can put the end wherever you want. Questions on this example? So I think if you get this example, this is, except for pointers, this is basically everything in simple IR. You'll be able to write simple IR, I hope, as well. Everybody good? Simple IR? Okay. All right, let me show you the grammar and give you an intro to what the Antler parser framework tooling will look like to actually process this in. It'll process this input for you, and then you'll write a little function for each of these constructs that will generate assembly code that will make the program equivalent for each of these constructs. Okay, this is the next slide, but it's a little hard to read here. Let me show it in the notes. Whoops. Uh-oh. I have a broken link. Actually, I'll just show it in here. Okay, here is the grammar for simple IR, written in Antler's grammar syntax. So Antler has its own notation for syntax. It works very similarly to the it's very similar to this grammar notation we saw last week. Instead of an arrow, it uses a colon, but this is saying that, for instance, if we have an assignment construct, the name of the construct is called assign. This is like sentence or noun in English. And it consists of a name followed by this notation, colon equals, followed by a name or a num. So name and num, these are terminals in this language. Name is defined to be a C identifier. Num is defined to be a sequence of ASCII digits. And so this grammar statement says the syntax of an assignment is name always followed by colon equals, and then followed by either name or num. Does that sort of make sense? So it's like an extended version of this syntax language, but it's doing the same thing. It's telling you what the structure is of all assignment statements. So this tells you all assignment statements will match this pattern. It'll always be an identifier name followed by this literal string, colon equals, followed by either name or num. Questions on this? Questions on this syntax? So operations are similar. Operations, so this is the name of the construct. It's called an operation. And its pattern is name followed by that same colon equal symbol, followed by name or num, followed by one of these 5 operator symbols, and then followed by name or num. Makes sense, right? Just variable name equals variable name or number, operator, variable name or number. So this defines the syntax of what all operation constructs will look like. Questions on this? All right, so let me go through the rest of these constructs, the rest of these statements that are in the language. So here's dereference, so name followed by assignment, followed by star name. Reference is name followed by assignment, followed by ampersand name. Assign dereference this is the one where you have star variable name, followed by assignment, followed by name or num. Here's the call syntax, name followed by assignment, followed by the call keyword, followed by function name, and this is just saying there's 0 or more names at the end of this function call. That's for the parameters. Here's label. Label is just name followed by colon. Goto is just goto followed by name. If goto is a little more complicated, but it looks just like our operators. It's an if keyword followed by name or num, followed by one of these 6 relational operators, followed by name or num, and then followed by goto and a label name. Questions on these? So this is just the syntax of the IR constructs. Yeah?
So when we call a function, are we not able to pass a num? We always have to pass a num?
Oh, yeah, that's right. Yeah, sorry about that. Did I say it was a num? Yeah, so the syntax only allows names. Yeah, that's right. That's right. Only allows names. And I think I also did this again for simplicity. So yeah, you're right. Good catch. It can only pass names. Yeah, and so strictly speaking, if you like your IR is not working, like Antler is complaining you have a syntax error, you can just consult this grammar to just validate whether you have a correct IR program. But yeah, good catch. Yeah.
Is this tool chain mainly useful for compilers, programming language parsing?
Well, so it's useful for parsing. So it's a parser generator, it's a parser framework. But you can use that for other things as well. So it doesn't just have to be compilers and programming languages. For like configuration file specifications, for protocol specifications, say network protocols, anything where you're dealing with text files that have any sort of structure to them at all, any sort of patterns that you need to enforce and you want to recognize, that's what grammars are good for. So yeah, depending on what you do in software engineering, you'll almost certainly use regular expressions to do pattern matching. If you've ever dealt with regular expressions, you can think of this as more sophisticated regular expressions. So yeah, this is used outside. So Antler is a super popular parsing framework, and people use it for more than just compiler writing. So that's why I use it, because it's kind of a generally useful, something to have in your tool belt as a software engineer. Other questions on this? Other questions on the grammar? So these are the terminals. This is what a name looks like. Has anyone done regular expressions? Did they do it? No, okay. Discrete 1? Maybe they wait to, discrete 2 might have regular expressions. Might be where they get into it. But these are just patterns that say letter followed by letter or number, any number of letter numbers. Number is just one or more ASCII digits. These are just naming the operators. And these are for white space and comments. So they'll just ignore white space and comments in your language. The structural part of this is pretty simple. So at the starting symbol, remember all grammars have a starting symbol. The starting symbol is a unit, which stands for compilation unit. A unit contains a single function. A function has the pattern function keyword, followed by a name, followed by local variables. The question mark just means it's optional. You don't have to declare local variables. Followed by parameters, also optional. Followed by 0 or more statements. Followed by a return statement. That's why the return statement can only appear at the end. Followed by the end construct. Local variables are just the local variables keyword followed by one or more names. Parameters are the same. Parameters keyword followed by one or more names. Return is return followed by name or num. And then end is just 2 keywords, end and function. And finally, statement is just one of these X number of statements. Questions on this grammar? Just kind of want to walk. You don't have to be an expert on grammars or parsing, but I just want to walk you through it so you at least are aware. And you can maybe look at this if, for instance, as your colleague pointed out, you're trying to pass numbers to a function call and the Antler parser is complaining to you that it doesn't work. But it's just think of it like a template that says what each statement must match in order to recognize that statement. Yeah.
Are pointers assigned to local variables?
Say again, are pointers assigned to local variables?
Are going to be on the local variables at the top? And then how do we know if it's a pointer or not?
Oh, like the type. Okay, so just like I say, all variables in this language are integers. There's no notion of a pointer type in this language, and this is actually true in C as well. It's a pointer if you use it as a pointer. In the same way, if you use addition on, say, a pointer value, on, say, like an address, well, the processor is just going to do the addition instruction that you've asked it to do. If you ask it to do a dereference, the machine is just going to dereference it. That's why you get seg faults or null pointer errors, because you've treated something an integer that you thought was a pointer, you've treated it as a pointer, and then the machine, doesn't permit that value to be treated as a pointer. Does that kind of make sense? So yeah, there's no type checking in this language whatsoever. As a bonus exercise, that might be fun, but it doesn't matter if you assign T1 to just some random integer. If you ask the machine to dereference it, it's going to try to dereference it. It's going to do the assembly operations to try to load that value from memory and read its value. Does that make sense? So yeah, and actually what I think is useful about writing a compiler, especially this back-end part, is you'll get a very up-close understanding of what pointers are in the language, and also what type checking does. So type checking just prevents operations that aren't supposed to be used on certain data. But strictly speaking, at the machine level, everything is just binary data. And so if you ask the machine to do an instruction like load memory from that binary data's that address given by that binary data, it's going to do it. It's going to let you do it. There's nothing stopping you from doing that, except like the segfault, checker. Yeah. So does that answer your question?
Yeah.
Okay. Yeah.
So what reason you don't have the star on T1?
Say again. Sorry.
What reason that you don't have a star on T1?
Here? Oh, here?
No.
Well, that's also kind of proving the point, right? Well, okay. So this is kind of correct C code, because if you ran this in C and you declared the types properly, T1 will now be the address of X. So T1 holds an integer no matter what, whether you store 0 in here, whether you store the value of X, whether you store the address of X. It's all an integer. And so I didn't put star on here because I wanted T1 to have the address of X. No, the address of X. I want to have the address of X here. And then I dereference it here because actually, so as a little quiz, what's the value of X after running this code? 11. X is 11 here, right? Because T1 is the address of X, and then I've dereferenced T1 and assigned that dereferenced address to 11. So this is like, I'm not trying to do wrong code here, but there's nothing stopping you from taking like T2 and dereferencing it, or taking X and dereferencing it to try to get address 11. The only thing stopping you is the system, which protects certain parts of memory. That's why you get a segfault or a null pointer error, because the hardware will not permit you to dereference that memory. Yeah.
But in the simple IO, you still have to specify that.
No, you don't have to specify its pointer at all. So remember, pointers are just integers. So you just give it the operation, and it'll just do it. The machine will do it. And this is why you get segfaults. So if you're getting segfaults because that's what you're doing. Yeah.
That's like I guess you could say if you're going to use a pointer, you just store the address first, and then.
Yeah, which is what we did here. So if you want to use it like correctly, then yeah, that's how you do it. Was there another? Yeah.
So do you even handle like the memory allocation static variable?
We'll get into that. We'll get into that when we get into functions after today's Wednesday, right? Yeah, so there'll be a break. We'll get into when we get into functions, how that works. So that's the more complicated part of, that and pointers are probably the most complicated part. We'll have to generate code that makes space at runtime for function local variables. And it gets a little complicated. And we'll also have to make sure that parameter passing works with other C functions that GCC and other compilers produce. Yeah.
In this representation, do you just add up like all the memory values of your static variables?
Yeah. So they don't have much space. If they're all 64-bit, then yes, you just take 64 times, or 8 bytes times the number of variables. Yeah, exactly right. That's how we're going to do it. Okay, so with that grammar, so now we have names. So this is what grammars do. They give us names for constructs. The constructs aren't told to us by the developer or by the speaker, but we have names for them now that match these patterns. And so in our compiler, what Antler gives us is a function that will run each time that construct is recognized. So we've got, enter is when you enter it, and so basically we'll do a tree traversal for you, and then when you've sort of the pre-order part of that traversal seen that construct, it'll run whatever code you give here in enter unit and function and all of these constructs. So if goto, it will run code whenever you see those constructs. So for instance, if we take I had a fully written compiler here, but let's blow away this compiler. Let me make sure I don't destroy my work. Okay, that's good. So here's my template here. So when I run this on basic.ir, your compiler template that I give you is going to do nothing. And so you'll take these semantic actions, these functions that will trigger whenever the parse tree sees one of these constructs, and you can start writing code in here. So for instance, I can say, I just saw, or I saw a, oh, let's not do it in reference because we don't have it. Where's return? So here's enter return statement. I saw a return statement. So this is the action I'd like to take whenever I see a return statement. So now when I run basic.ir with my compiler, that statement will get triggered. If, for instance, I do that for an assignment, and I say, printf, I see an assignment statement, for this input program, what do you expect to happen? What should my compiler print out for this input? So I've got function, return, end function. And for my semantic action for assign, I say I see an assignment statement. For return, I saw a return statement. What should be printed out when I run my compiler on this? Anything else? No, right? Just that. If instead I add an assignment statement, and remember, there's no type checking here. The compiler doesn't know or care. At this point, the parser doesn't know. I added an assignment statement here, and now that semantic action triggers. That code that I wrote triggers. So that's why this parser fragment is so useful, because you don't have to worry about processing the input language, traversing the tree. It'll do all that for you, and then you just have to focus on what code to generate in each of these semantic functions. So you'll literally write code. This is C++ code, but you'll write code that will literally output assembly code. So something, I mean, it won't necessarily do this, but this might be one example of what gets output. So now when I run this, you'll see I literally get assembly code being output. So we've already started compiling. The whole trick will be to take pieces of the input, like the name that's being used, like for instance, I don't actually remember how to write this, but take things like the name that's being used. Let's see if I broke this. I broke it. Well, you'll be able to actually take the name from the input. Oh yeah, I'm bad at C++. And actually start printing out pieces of the parse tree and use that to build up assembly code that will be equivalent. All right, everyone. So, okay, I kept you 1 minute over. Everyone have a good break. Yeah, what's your question? Actually, no, it doesn't matter. It'll be easier with cout though. Sure.